Why medieval wells stayed clean for 500 years while modern water goes bad. In 2019, researchers in England tested water from a medieval well that had been sealed since 1485. The stone-lined shaft, 40 feet deep and untouched for over 5 centuries, still contained drinkable water. Meanwhile, bottled water in your pantry grows bacteria after opening. Municipal water develops biofilm in pipes within months. And plastic bottles leach chemicals after sitting in the sun for an afternoon. A well built by illiterate peasants with hand tools outlasted a modern infrastructure system engineered by professionals with university degrees. The medieval well wasn't just functional, it was superior in ways that challenge everything we assume about progress and sanitation. The answer isn't magic or luck. It's a combination of material science, depth engineering, and natural filtration that we've systematically abandoned in favor of chemical dependency. The stone factor. Medieval wells weren't just holes in the ground. They were precision-engineered shafts lined with carefully selected stone, usually limestone or sandstone, stacked without mortar in a technique called dry stone construction. The stones were cut to fit tightly, creating a permeable but stable structure that allowed water to seep in while filtering out larger contaminants. This wasn't accidental. Medieval well diggers understood that certain stones inhibited bacterial growth while others promoted it. Limestone, the most common choice across Europe, contains calcium carbonate that naturally raises water pH to slightly alkaline levels between 7.5 and 8.5. This alkalinity creates an inhospitable environment for many pathogenic bacteria that thrive in neutral or acidic conditions. Modern research confirms what medieval builders knew empirically. Water stored in limestone containers shows significantly lower bacterial counts than water in plastic or metal. A 2015 study from the University of Bristol found that water in limestone vessels maintained bacterial counts below 100 colony-forming units per milliliter even after 6 months, while plastic containers reached over 10,000 CFUs in the same period. The dry stone construction also mattered because it prevented stagnation. Water seeped through tiny gaps between stones, creating constant microcirculation that oxygenated the water column. Oxygenated water resists anaerobic bacteria that cause foul odors and dangerous infections. Modern wells often use concrete or plastic linings that create completely sealed systems. Without microcirculation, these wells become breeding grounds for biofilm, sticky colonies of bacteria that coat surfaces and continuously shed into the water supply. You can chlorinate all you want, but biofilm protects bacteria from chemical treatment, allowing them to persist and multiply once chlorine levels drop. Medieval builders also knew to avoid certain materials. Iron nails or fittings were rarely used in well construction because they rust and leach into water, promoting bacterial growth and creating metallic tastes. Modern wells frequently use steel casings that corrode over time, releasing iron oxide that feeds bacteria and discolors water. The medieval approach was passive and permanent. Once built correctly with proper stone selection, the well required minimal intervention to maintain water quality, depth, and temperature. Medieval wells weren't shallow. Most ranged from 30 to 100 feet deep, with many reaching 150 feet or more in areas with low water tables. This depth wasn't just about reaching groundwater, it was about reaching cold groundwater. At depths below 20 feet, earth temperatures stabilize at roughly 50-55 degrees year-round in temperate climates, regardless of surface weather. This constant cold temperature fundamentally changes how water behaves. Cold water holds less dissolved oxygen, which sounds negative until you realize that most pathogenic bacteria require oxygen-rich environments to multiply rapidly. The reduced oxygen at cold temperatures slows bacterial reproduction to a crawl. E. coli, for instance, doubles every 20 minutes at 98 degrees, but takes over 24 hours to double at 50 degrees. That's a 72-fold reduction in growth rate just from temperature control. Medieval wells were essentially natural refrigerators, keeping water in a perpetual state of bacterial dormancy without any energy input or chemical treatment. The depth also created pressure filtration. Water reaching a 100-foot well has traveled through multiple layers of soil, clay, sand, and rock, each serving as a physical filter. Modern hydrogeology recognizes that every 10 feet of soil removes approximately 90% of bacteria from infiltrating water. By 100 feet, the filtration effect is so complete that water emerges essentially sterile, even if surface water is contaminated. Medieval communities intuitively understood this principle by digging deeper wells in areas with known contamination issues, even though they had no concept of bacteria or microbiology. Compare this to modern water systems that often draw from surface reservoirs or shallow aquifers, then rely entirely on chemical treatment to eliminate pathogens. When treatment fails, due to aging infrastructure, human error, or system overload, contamination spreads rapidly because there's no natural barrier between the source and your tap. The 1993 Milwaukee cryptosporidiosis outbreak sickened over 400,000 people and killed 69 because the water treatment plant failed to filter properly. A deep medieval well, by contrast, would have naturally filtered out the cryptosporidium parasites through dozens of feet of earth. Natural filtration layers. The earth itself is a filtration system that medieval well diggers learned to exploit. When they dug wells, they weren't just digging through dirt. They were navigating through distinct geological layers, each with specific filtration properties. The uppermost layer, topsoil, is actually the worst for water quality. It's rich in organic matter that feeds bacteria, and full of surface contaminants from animal waste and decomposing material. Medieval builders knew to line this section completely with stone to prevent any surface water infiltration. Below topsoil lies subsoil, a denser layer of clay and silt that acts as a primary bacterial filter. Clay particles are negatively charged and attract positively charged bacteria, effectively trapping them through electromagnetic adhesion. A well-designed medieval well would have its upper 15-20 feet lined with impermeable stone to bypass topsoil and subsoil entirely, allowing water to enter only from deeper geological layers where natural filtration had already occurred. The next layer, typically sand or gravel, provides mechanical filtration. Water moving through sand travels through tiny spaces between grains, and any particle larger than those spaces gets trapped. Sand filtration removes not just bacteria, but also larger parasites, suspended sediments, and organic matter. Modern slow sand filters, used in some water treatment plants, are essentially artificial versions of this natural process, but they require regular backwashing and maintenance that natural sand layers never need. Deepest of all, many medieval wells reached fractured bedrock or limestone aquifers. Here, water has been underground for years or even decades, traveling through miles of rock fissures in complete darkness. This extended underground residence time matters because it allows natural die-off of pathogens. Most bacteria and viruses can't survive more than a few weeks without nutrients or hosts. By the time water reaches a deep aquifer, it's been effectively sterilized by time itself, a passive disinfection process that requires nothing but patience and depth. Modern water systems bypass these natural filtration layers entirely. We pump water from rivers or shallow reservoirs, pipe it to treatment plants, dose it with chlorine and other chemicals, then send it through miles of aging pipes where it picks up new contamination from biofilm, pipe corrosion, and cross connections. The water that reaches your tap has been artificially cleaned, but is constantly exposed to recontamination. Medieval well water, once filtered by 100 feet of earth, stayed filtered because it never left the protected environment of the stone-lined well shaft. Material matters. The materials medieval builders avoided are just as important as what they used. No plastic, obviously, but also no lead, no copper in large quantities, and minimal iron. Each of these metals leaches into water and creates problems that stone simply doesn't. Lead piping was used by Romans, but largely abandoned by medieval Europe, possibly due to observed health effects even without understanding lead toxicity. Stone wells eliminated this risk entirely. Modern homes built before 1986 often still have lead solder and copper pipes, and even newer homes can have lead in brass fittings. The EPA allows 15 parts per billion of lead in drinking water, a level medieval well water naturally achieved through stone construction without any regulatory framework. Copper is antimicrobial in high concentrations, but it also promotes specific types of bacterial growth at lower levels and can cause digestive issues. Medieval wells avoided copper entirely. Modern plumbing systems use copper extensively, and while it initially inhibits some bacteria, over time it corrodes and creates uneven surfaces where biofilm can anchor. Studies show that copper pipes develop biofilm within 3 to 6 months of installation, reducing water quality despite copper's antimicrobial properties. Plastic is the modern disaster that medieval builders never had to consider. PVC pipes, plastic storage tanks, and polyethylene bottles all leach chemicals into water: BPA, phthalates, antimony, and various microplastics. A 2018 study found microplastics in 93% of bottled water samples worldwide. These particles carry bacteria, disrupt endocrine systems, and accumulate in human tissue. Stone doesn't leach, ever. A limestone well built in 1200 AD leaches exactly the same amount today as it did 800 years ago, none. Wood, when used in medieval wells, was carefully selected. Oak was preferred for its density and tannin content. Tannins are natural antimicrobials that inhibit bacterial growth and give water a slightly astringent quality. Some medieval wells used oak lining in the upper sections where stone was difficult to work with. And these oak timbers, when excavated centuries later, show remarkable resistance to rot precisely because the tannins prevented bacterial colonization that causes decomposition. Modern treated lumber uses chemical preservatives that leach into water, making it unsuitable for potable water systems. Community oversight. Medieval wells weren't just physical structures, they were social institutions with strict rules and communal maintenance. Most villages appointed a well keeper, someone responsible for monitoring water quality, preventing contamination, and organizing repairs. This wasn't ceremonial. Well keepers had real authority to fine or punish anyone who polluted the well, whether through dumping waste, allowing animals too close, or drawing water with contaminated buckets. The concept of well sanctuary existed across medieval Europe, a protected zone around each well where certain activities were forbidden. No animal slaughter within 50 feet, no waste disposal within 100 feet, no construction or digging that might disrupt underground water flow. These rules emerged from observation and experience, not scientific knowledge, but they worked. Modern wells often lack any protected zone, sitting near septic systems, agricultural fields, or industrial sites that continuously threaten groundwater quality. Communal maintenance meant that wells were inspected regularly and cleaned promptly when needed. Medieval records describe annual well cleanings where the shaft was emptied, scrubbed, and inspected for cracks or contamination. Compare this to modern private wells, which many homeowners never inspect or maintain until something goes wrong. According to the CDC, only 15% of private well owners test their water annually, and many have never tested it at all. The social structure also prevented overuse. Wells had daily schedules. Morning water was for drinking and cooking, afternoon water for livestock, evening water for washing. This staggered use prevented depletion and allowed the well to recharge overnight, maintaining water quality. Modern municipal systems operate 24/7 at maximum capacity, constantly drawing water faster than aquifers can naturally recharge, leading to water quality degradation and aquifer depletion. Modern water problems. Municipal water treatment relies almost entirely on chlorination, a chemical process introduced in the early 1900s that revolutionized public health by killing waterborne diseases. But chlorination isn't preservation, it's temporary disinfection. Chlorine kills most bacteria on contact, but it also dissipates quickly. By the time water travels through miles of pipes to your home, chlorine levels have dropped significantly, especially in dead-end pipes or low-use areas. When chlorine drops below effective levels, bacteria regrow rapidly, often reaching higher counts than before chlorination because competing microorganisms have been eliminated, leaving unlimited resources for survivors. Chlorine also creates problems it was meant to solve. It reacts with organic matter in water to form trihalomethanes, THMs, and haloacetic acids, HAAs, both classified as probable carcinogens. Long-term exposure to chlorinated water increases bladder and colorectal cancer risk, according to multiple studies, including a comprehensive 2016 analysis in Environmental Health Perspectives. Medieval well water had zero THMs or HAs because there was no chlorination. The water never needed it thanks to natural filtration and cold storage. Aging infrastructure is the other crisis. Most municipal water pipes in the U.S. were installed 100 years ago and are corroding from the inside. Cast iron pipes develop tuberculation, crusty buildup of iron oxide that harbors bacteria and reduces water flow. These tubercles create pockets where bacteria multiply protected from chlorine, then periodically shed into the water stream, causing brown water events and quality failures. Medieval stone wells don't corrode. The stone is already oxidized and stable, providing a permanent surface that doesn't degrade or leach over time. Plastic bottles, marketed as clean and modern, are actually bacterial incubators. Once opened, bacteria from your mouth contaminate the bottle, then multiply in the warm water. Studies show that reused plastic water bottles can have bacterial counts exceeding toilet water after just a few uses. The plastic itself degrades under heat and UV exposure, leaching endocrine disruptors into the water. Glass would be better, but stone was best. Completely inert, naturally cool, and antimicrobial through alkalinity. The knowledge gap. We lost the skill of building proper wells, not because the technology became obsolete, but because centralized water systems seemed more efficient and modern. Cities expanded beyond the capacity of individual wells, and municipal systems offered convenience and standardization. But convenience came at a cost: dependence on complex infrastructure, vulnerability to systemic failure, and loss of understanding about how water naturally maintains quality. Modern drilling technology can reach much deeper than medieval hand-dug wells, but we use this capability to drill narrow boreholes that we immediately case in plastic or steel. These boreholes bypass natural filtration, but also eliminate the temperature regulation and mineral contact that stone-lined wells provided. We've optimized for depth and volume while ignoring water quality beyond chemical treatment. The knowledge of reading geological layers, selecting proper stone, and positioning wells for optimal natural filtration has largely disappeared. Modern well drillers follow regulations about depth and casing, but few understand the hydrogeology that medieval builders learned through generations of observation. When you drill a well today, you're likely to get a 6-inch plastic-lined borehole with a submersible pump, functional but completely dependent on electricity and vulnerable to contamination if surface water enters the casing. Some communities are rediscovering these principles. In parts of India, traditional step wells, similar to medieval European wells in principle, are being restored and integrated into modern water systems. These wells combine depth, stone construction, and community oversight, providing reliable water without chemical treatment. Studies show that restored step wells have better water quality than nearby tube wells despite being hundreds of years old. The restoration work reveals something important. These wells don't stay clean by accident. They stay clean because they were built with materials and techniques that work with natural processes rather than against them. The stone doesn't just line the well, it actively improves water quality through mineralization. The depth doesn't just reach water, it provides filtration and temperature control. The community oversight doesn't just protect the well, it prevents the contamination that requires chemical treatment in the first place. Medieval wells succeeded because they were designed as complete systems, not just holes with pumps attached. The stone construction provided alkalinity and structural integrity. The depth delivered cold temperatures and natural filtration. The community protection prevented contamination at the source. And the absence of modern materials like plastic, copper, and treated lumber eliminated leaching and biofilm formation. Every element reinforced the others, creating a water system that required minimal intervention to maintain quality over centuries. Modern water systems do the opposite. We deliberately bypass natural filtration, pump surface water full of contaminants, treat it chemically, then send it through materials that degrade and leach. We've replaced passive, permanent solutions with active, temporary ones that require constant energy input and chemical addition. The result is water that's technically safe according to regulations but demonstrably inferior to what medieval peasants drank from stone-lined wells. The lesson isn't that we should abandon modern infrastructure and return to hand-dug wells, but we should recognize that medieval builders solved problems we're still struggling with. They created systems that purified water without chemicals, stayed cold without refrigeration, and lasted centuries without maintenance. Those aren't primitive achievements, they're sophisticated engineering solutions that we've largely forgotten in our rush toward technological complexity. The medieval well stayed clean for 500 years because it was built to work with nature, not against it. Modern water goes bad because we've chosen convenience over durability, chemical dependency over natural processes, and complexity over elegant simplicity. The technology to build better water systems already existed 800 years ago. We just stopped using it. If this changed how you think about water quality and what we've lost, hit subscribe. We're digging into more medieval methods that modern society abandoned too soon. Drop a comment if you know of any old wells still in use, and share this with anyone who thinks older always means worse.